Hello everyone, it's Red Gadget here, and we have another video for you. So today is this part 2 of the machine learning series in terms of training an AI model for Edison Format. So yeah, it would be cool to maybe have a model that can actually predict the outcome of a game while the game is going on, or maybe even play the game. But so far we're training a model on the opening 6, so on the opening 12 for both players basically. And we're also having another aspect, which is the person who went first, and we're trying to see how much does that influence actually the final decision of the model. Yeah, so this is part 2. There was part 1, if you haven't seen it already. It's where we explain kind of how the data is used and how we train a simple classifier model. So in that case, it would be the random forest model with the help of XGBoost. But in this video, we will do a neural network approach, right? So we'll choose a different architecture to see how that performs. And last time our results were not that good, so approximately the accuracy was around 61%, which is still good because at the end of the day we're trying to predict just from the opening 6. And Yu-Gi-Oh! Is such a complex game where a lot of things can happen in one turn, like top decks can happen or misplays can happen, right? So a lot of things can happen, and having a 61% accuracy just from the start is actually pretty high. Now, yeah, we had the fact that the going first also indicates around 60%. However, our model is better at predicting the winner because it also takes into the account the hand. And if you have a really good hand, even if you went second, the confidence of the model in you winning would be higher for yourself rather than your opponent, even if your opponent's going first. Now, yeah, with that being said, we had the results from part 1, and we said that, yeah, this was not so good. We're trying to push this more. We're trying to, increase the accuracy of the model, so we need to go deep, we need to go bigger, and for that, we need to step away from these kind of random trees or random forest models and go into a neural network. So the neural networks are something that would help us basically generalize better. So it would try to explain away the fact that going first is a big aspect of the final prediction, and maybe try to capitalize on the fact that we have 12 data points for the cards in hand, and maybe try to use that to further improve the final prediction. And we need a bigger model for that, obviously. So yeah, with that being said, this was what we announced in part 1 at the end. And yeah, going into the data, again, it's the same data. You can see here the 6 cards for player 1, and then 6 cards for player 2. And finally, you have the first player, the player that goes first, and then we have the winner column. So we're, again, using these 13 values here to predict the 14th value, which is the winner itself. Now, again, computers don't really understand, and such models don't really understand this text, like solemn judgment means nothing to it. So we need to encode it in some kind of numeric format. And in this case, that would be just like numbers indexed based on which card in the... Like if you were to compile all these cards into one place and just take them in order, it would just be the order of the card, right? So nothing all that confusing. I just wanted to show off that that these two things are basically the same. And yes, we are reading this, but the computer is reading this. We have around 700 or 800,000 games. So one row is one game. And yeah, 14 columns, obviously, for 12 cards going first and the winner. But so for the last project, I was fearing that going first variable might have a lot of impact on the final prediction, because as we saw 60% is just an average statistic. It's just a statistic for going first and winning, but we had around 61% accuracy for the model. So maybe the model is just focusing on the going first and then kind of forgetting or minimally taking into account the other cards. So for that, I decided, let's just kind of skip this column, right? Let's drop it and let's train the model just only on the cards. And since we have a neural network, or a deep neural network, we should have enough expressiveness to actually maybe get some meaningful insight from these 12 cards in order to predict the winner. And Yeah, so I wanted to also get into a bit of explaining on what is deep neural network and deep learning. So yeah, ChatGPT actually, it's kind of funny that like a model explains what it is. But yeah, anyhow, ChatGPT gave me this definition, which is it's a type of machine learning that uses layered neural networks, which is this what you see on the bottom, to automatically learn complex patterns from large amounts of data. So we have large amounts of data. We need complex patterns, right? Opening hand is pretty complex when it comes to predicting the final outcome, especially since we don't have additional information such as the turns after. And yes, we want to use this basically architecture as seen here. What we used before, so XGBoost, is kind of like traditional machine learning. So this is kind of new fancy deep learning stuff, like ChatGPT, all these new models that you see, they use kind of this. But previously we used a traditional machine learning system, which is these kind of random forests. So you could just imagine this is called a tree, and if you flip it upside down, it looks like branches going up, right? So it's just kind of like, okay, is this card a part of the Blackwing archetype? Okay, it is, for example. Let's put it in this bucket. If it's part of frogs, let's put it in this bucket. And then it maybe assigns weights to these buckets, and it's just basically a lot of branches, right? So it's just learning branching, while neural networks connect each of these neurons here, these little dots, to the other ones, and then you can build like complex structures, right? So this is more traditional and very easy to use and to run, but deep neural networks come in all shapes and sizes, and some of them are huge. So for example, for GPT-3, it has what is this, 175 billion parameters. GPT-3, as you can see here, 175 billion parameters, as it says here. But for example, GPT-4 has like, what is this? This is like a, wait, this is like a million, billion. I don't know these numbers. It's a huge number. It's like a trillion. It's like 100 trillion or something. I don't know. And then you have GPT 3.5 Turbo, which has around 20 billion. So as you can see, it's a huge number of parameters, which means huge number of these little connections here. And the reason why I'm explaining this, it's because something being a deep learning neural network doesn't mean that they're always all the same. So we cannot train something like this, clearly, because we don't have the infrastructure. I mean, these models are trained on huge clusters that have thousands, if not hundreds of thousands of computers and processors. So what we can do is train around 700,000 parameters. So we could train a neural network. The one we trained has around 700,000 parameters. So with that being said, it still looks the same. It's just a lot smaller, right? And the ones that like big companies train, like ChatGPT, for example, or other models that are used in, for example, medical fields, they're just gigantic. They have billions and millions and trillions of parameters, but we cannot do that. So what we have around, let's say, 1 million parameters, and we want to train the model. And we can very easily do it. I wrote the code, and yeah, we can just train the model. And it takes around a few minutes to complete. And yeah, as you can see, while it's running, just subscribe. Like before we see the results, click the subscribe button, and there's also Patreon in the description. So if you're interested in supporting, I'll leave a link down below. But yes, now that we have trained the model, and took around 15 to 20 minutes, on my laptop, like a MacBook, a regular MacBook Air, so nothing special, we get the following results. So keep in mind that the accuracy of XGBoost from part 1 was 61%, as we discussed, but the accuracy of our new model, without the taking into the account who's going first. So let me go back. So we are not training on this column, but the model to the right, the model from before, was trained on this column. So this model is just trained on the cards, and it has around 59% accuracy. So this means that actually we can get the 9% accuracy in prediction in terms of a model, because I think humans, they cannot really comprehend this whole data set, and when they look at the people playing cards on the field, they say, oh yeah, this player will win. But having a model trained to do just that, it's far more accurate than a player saying, oh yeah, he opened 2 whirlwinds. Because there are some connections that we don't really see, for example, while the model has seen that much data that its accuracy is almost like a guarantee of who might win. Not exactly, but in this sense, we could say, okay, 59% is the probability of a certain player winning given the hands, right? And yeah, so this means this 9% actually is just a bonus of how good you open compared to your opponent. We don't really know who's going first and who's not going with these results. But yeah, that being said, around 59 to 60. However, now that we have this, why not just leave this column in and train again and see what is the difference between these two models? So again, the model is not that huge. As I said, around 700 K parameters, but I think it still expresses well enough to the point of where we can reach with this project, right? We don't really have access to such high computation power. So yeah, let's keep this this column in, and now let's train. So we get again 61% here, but this is almost 60. If we round, it's like around 63%. So yeah, we have kept the column in, and we have gotten 4% improvement. So this is kind of helping us in terms of understanding, okay, also if a person is going first and opens well, they might have 63% chance of winning, for example. If this model is as good as it is, which given 700 or 800 games is a huge amount of data, so I don't think it's like having issues in terms of, okay, not having enough data, so just kind of making stuff up, to put it that way. So to summarize, yeah, weak model from before, a random forest model, 61% accuracy. Strong model like a neural network that we have now, 59% accuracy just on the hands. And then a strong model like a neural network with the hands and who goes first, 63% accuracy. So as we can see, the influence of who's going first is 4%. But then we have the statistics that say if you're going first, you should win 60% of the time. But if you have hands plus the person who goes first, you can actually boost this up to 63, because these things often, if you open good and you go first, it's like these things are not really like these things depend based on the outcome, right? So the outcome depends kind of on both, and we have 63% basically prediction of with the stronger model, prediction of the opening hands plus who goes first. So if you go first and you have a very good hand, your chances of winning based on the model on average would be, for example, 63%, right? So 63% is what the model predicts, in how many percentages the model predicts correctly the outcome. And yeah, so that would be pretty much it. I hope you enjoyed, and yeah, if you didn't, that's okay. And yeah, I hope you enjoyed this. This is kind of where we end the machine learning journey. So in part 3, we will do some statistics on this data set. And yeah, so we'll take raw statistics, and we will try to calculate some win rates and some differentials and some values, a lot of values actually across all kinds of ELOs, all kinds of play rates for certain cards. So if a card's not really played, like a Jama Green, there's no reason for us to really look at it, right? We know it's bad. But if a card is played, so across different play rates, then we would want to see if a card is bad or good, right? So in the card pool of the, let's say, meta decks. And then, but we'll also do it across general, just all cards. And yeah, so best and worst cards. And here the example is like, for example, top 20 cards in this like meta range, and it's just for example, Trap Dust Shoot is first. This is a little teaser, and yeah, this is pretty, like, everyone knows this, right? Trap Dust Shoot's like win rate 58%, and in part 3 we'll see like this for many different cards, right? So stay tuned for that, and make sure to subscribe in the comment section below. And with that being said, I'll see you in the next video. Peace.